I'm a fan of the opera.
Okay, welcome everybody to the Kingston Center May meeting. I'm filling in for Malcolm because we all know where he is. And we are all very envious, but that's okay. We will carry on. Here's the agenda for this evening. So we're going to welcome members and any guests that are here this evening. And this meeting is not on Zoom, but we are recording it on phone, and we will upload it at a later time. So we have announcements. Our guest speaker will have a 5-minute intermission. What's up in the sky with Rick? And if anybody has brought in anything that they want to show, you can bring it up at the break, and we'll load it up. Okay. All right. So announcements. Wednesday we have our Zoom socials, which is an opportunity for the members to chat and discuss what they're up to. Join the email chat list to get the Zoom invitation, and it's posted to the center's email list. Any new members that need help getting set up on the chat list, let us know. The Kingston Monthly Newsletter Regulus is found on our Kingston Center website, and I do know that the editor is working on a combined issue. Science Rendezvous is this weekend on Saturday, May 11th. And Kevin and I will be there about 8:30 in the morning to set up. It starts at 10, but we'll get the tent. And if it's raining, then we'll think about moving everything inside and set up tables and have handouts and the whole bit. At night is the Queen's open house. It starts at 7:30. Susan will have an info session on the summer star party. Oh yeah. And then John is going to come up and give us a bit of a talk on the RASC-GA. So Susan, if you want to come up and talk about the spring star party.
No rain on Saturday.
Good. We don't want rain on Saturday.
No, I just said no rain. No rain on Saturday.
Okay, I'm going to hold you to it.
Okay, so a couple of weeks ago, the topic of the spring version of Fallen Stars came up, and we thought that it was all, everybody had decided to, no, we wouldn't do that. But I got an email from downtown, and I forwarded it to the list for everybody to see. He would like to know by May the 20th if there's any interest at all in going to South Bay in the county for the weekend of June the 7th, I think it is, 6th and 7th, something like that. So check your email and see the note. It'd probably be a slightly, if possible, less sophisticated weekend than the fall weekend. But anyway, so May the 20th is his cutoff date for that. One other thing, the email message is please reply all. So reply to the chat list so people know that people are interested and somebody might show up. And it will also go to downtown in Belleville. The other thing that I would like to mention tonight is it's just an idea, and I just wanted to put it out there. The center has in the storage shed several optical tubes that could make fine little Dobsonian telescopes. I would like people to consider giving one of those optical tubes a home and possibly think about building a little Dob out of those an optical tube. And so that's just making the basic Dobsonian components to hold it, and cleaning the mirrors and stuff like that. If you've never done anything like that, it doesn't matter, because we have nothing to lose with equipment that is not otherwise being used. If you can learn how to do something like that, if you want to tackle something new, think about it. I haven't run this by the president or any of the other executives. But just think about it, and that's all I have to say.
Okay. Thank you, Susan. John, would you like to come up and give a bit of a talk on the GA?
Hello. Should I use that?
Yeah, it helps.
Okay. Hello, everyone. As many of you know, this past weekend, the Royal Astronomical Society of Canada held their annual GA, and it was a Zoom event this year. It was just a Saturday, Sunday thing. It was thrown together kind of at the last minute. The staff at National Office has been pared down greatly this year to just 3 people, and they had just finished the annual audit of the last year's books, which wasn't as bad as some had feared. But more on that later. This year's GA they were mainly many of the talks were from everything was from members, and they were talking about what they've been doing in their local centers and themselves observing projects, astrophotography, that sort of thing. There was some videos, I think it was 5 or 6 centers submitted videos of their center observatories and their observing sites. Many of those videos were very interesting and very informative. It was interesting. Attendance was generally in the neighborhood of 80 to 100 people on Zoom. It varied. There was also a seminar on green laser pointer usage, which I believe there's 4 of us that are now authorized to be using a green laser pointer.
Use the word certified.
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 Many of us are, yes. To use, technically, it is illegal to point a laser pointer into the sky at night unless you have authorization and certification. National Office of RASC has a special waiver with Transport Canada to allow that under certain conditions and certain places. You have to be, more than 10 kilometers or 10 miles away from an airport. There's a map, online interactive map, that will show you where the radiuses of these zones of exclusion are. You would need 2 people that were certified to be using the laser pointer, one to be operating the laser pointer and one to act as a spotter to make sure you don't accidentally point it at an aircraft. And they also have to be, and there is a maximum wattage of 5 milliwatts authorized to be used. Anything larger than that is not to be used, period. Now, many of those things are available from various retailers, but if you were to ever get questioned about the use of, you will be paying a large fine. So be careful. And anybody's interested, we will be, there is a program where we can, the centers will be able to authorize more people to be using the green laser pointer. There is a test. In Transport Canada's world, don't worry too much. It is corrected to 100%. So, you take a little bit of time, go through the rules and regulations, and everybody can be done if they would like. It also has to be used at an authorized RASC event, which means you have to give the center notice at least a minimum of 8 hours in advance, and then a report needs to be submitted later with some detail on number of people attending and stuff like that. That way we can tell Transport Canada that we've been using this authorization this many times, this often, this many places, and they can determine whether it's worth their while to allow it use continuation, or they can say, oh, you're doing this too often or too close, and whatever goes through their minds. But the GA was fun. The next big event for National will be the annual general meeting, which will be the end of June. I'll post some details about that in the list. But basically, that will be a report from the National Board about everything the Society has been up to. Accounting to some degree, I hope to a great degree, about what the financing has been like and where they're going. There is no talk about a fee increase yet for next year, but the board reserves the right for that, I've been told. Apparently, they're going to consult National Council about that this time, but that hasn't happened yet. So hopefully there might not be a fee increase coming this year. there is, like I say, I hear some moans about that before. If anybody has any questions or concerns or ideas for national, please let me know, and we'll see about how to pass it on. This society, Astronomical Society, is made up of the members, and we are the members. So anything we would like to see done or not done or done better, we can certainly. We're always looking for volunteers with ideas and a little bit of will to help see things through. More help makes it lighter work for everybody, and and hopefully we can carry on. Thank you.
Thanks, John. Okay. Next, I'm going to introduce our guest speaker, Dr. Sarah Sadavoy, who received her degree in astronomy from Victoria, University of Victoria in 2013. And her research areas, this is right off the website, sorry, but the earliest stages of star formation and planet formation, including fragmentation processes, dust grain formation and evolution, gas chemistry and the origins of life, the formation and evolution of protostars, the role of magnetic fields in star and planet formation, and the differences between low mass and high mass star formation. To explore these processes, she has used observations from telescopes from all over the world to investigate the star-forming regions through continuum spectral line emission and polarimetry observations in the infrared, sub-millimeter, and radio bands. So tonight's topic is the far infrared sky, a look back with the Herschel Space Observatory. Let's introduce Dr. Sarah Sadavoy.
Gentleman and this lady right over here are just putting together a new dome, and I would humbly suggest that you start your talk with a picture of the new Vic dome.
Oh, I don't have it on me.
Oh no!
I can describe it.
That would be good.
Okay.
And I have a wireless.
I can definitely describe that. I do apologize that I don't have the Vic dome on me, or at least I don't have it like easy access. All right.
There we go.
Yep, hold on. What's it doing? One sec. Oh, it doesn't have mirror displays on. There we go. Can you hear me okay?
We'll find out later.
All right, well, sounds good. So I've been asked to speak about the UVic dome. So the UVic dome has this really awesome happy face on it. It's just two big circles for eyes and a big smile. And then on Halloween, they'll put fangs on it, which was a really awesome prank to come to campus and see that someone had put little black construction paper fangs on the happy face for Halloween. So yes, if you are able to get on the outside of your dome easily with a bucket of paint, I encourage you to have some fun with it. Not with a dome is the Herschel Space Observatory, which was, as you can probably tell from its name, in outer space. And this was a facility that I used heavily for my PhD. And so back in the era of my time at UVic, that was something that was near and dear to me. And so what I want to do right now is do a little bit of a look back at what Herschel has given us and why we look at the far infrared sky. But another thing I am trying to do is to center myself not just in the universe, but here on Earth. We are, of course, in Kingston, which is the ancestral lands of the Anishinaabe, Haudenosaunee, and Huron-Wendat people, as well as many other Indigenous people who live here or have lived here over the course of all of history. And when I was in Victoria, we didn't think about the land as much as we are moving towards right now. With space telescopes, you don't have the same sphere of influence in that sense. So one thing I've been trying to do is also position myself on the lands of the telescopes that I use. However, Herschel being a telescope that was in an international collaboration between the European Space Association, NASA, and the Canadian Space Association, I recognize that there are many indigenous lands for which the peoples who built that telescope and launched it need to acknowledge. So where I am right now here in Kingston, I am using other facilities than Herschel, because Herschel is no longer active, but I recognize that there are many lands from which people who worked with Herschel and helped build Herschel have indigenous peoples who lived in those lands. And so a really good way of finding out where various different First Nation groups have lived and where they continue to live is this nativeland.ca website. So it's where I tend to go to when I want to know, the history of the lands that my telescopes happen to sit on. So I've used the word was a lot, and that is unfortunately the case with Herschel. It did have a definite lifetime, so it is no longer active. So the last time I actually gave a Herschel talk, it was still is. So it's a little sad for me to be using was, and if I switch into present tense by accident, please forgive me. But Herschel was a 3.5 meter far infrared space telescope, and prior to James Webb, it was the largest infrared telescope in space. So Webb, of course, eclipsed it by quite a bit in terms of mirror size. So 3.5 meters, of course, being the diameter of the mirror, which you can kind of see the dish right here. But at the time, it was revolutionary, and the science that we're getting from it is still quite revolutionary. So it was launched back in May of 2009 by the European Space Association, and it was sent to Lagrange point 2, L2, which is actually where James Webb is right now. So it's kind of like, one moved in, one moved out in that respect. And it was a far infrared telescope that had 3 instruments. So that is sort of a artist's rendering of what Herschel looked like. So you'll see this feature right here at the end. This was the sun shield. All right, so the sun shield was always pointed towards the sun. Because you're observing at far infrared wavelengths, you want to keep your instruments as cold as possible. So they would try to block the sun with the sun shield so that you constantly maintained as cool a temperature as you possibly could for the mirror itself. Because if the mirror is warm, you will not see any science targets. So the mirror was generally at a temperature of about 70 Kelvin, so it was kept quite cold. The instruments, of course, are housed inside with cryostatic cooling down to like below a Kelvin temperature. These were very cold instruments. But this is just to kind of give you an idea of what the telescope would have looked like when it was in space. So why do we go to far infrared wavelengths? Well, the answer is we get a very different perspective of the universe. So this is the electromagnetic spectrum. This is every form of light that exists. You've got the shortest wavelengths, highest energy gamma rays to X-rays and UV. Visible light is this narrow swath right here. And then as you go to longer wavelengths and lower energies, you've got the infrared and the radio. Why we go to other wavelengths with telescopes of various different types is, again, as I say, to see things that we would not normally see with just focusing in on the optical. So a nice example I'd like to show is this pair of burritos. All right, here you've got the optical view. This is what your eyes would look at when you're looking at the burritos. So this is visible light, and you can only see the outside, all right, because you can't see through an opaque object in visible light. But if you look at the same pair of burritos in the infrared, you can start to get an idea of what's going on inside of them. You can see the temperature, the heat inside of it. Specifically, you can see you've got hot pockets and cold pockets, and that might tell you something about the distribution of the beans and the rice and the vegetables. And so you could start to make a model of what's inside the burrito thanks to the infrared light. So infrared light lets us see things we normally would not see. Now, this is a pair of burritos. Let's look at the sky. I'm sure all of you are familiar with this object right here. This is, of course, Orion. I took this from WikiSky. This is observations from the Digital Sky Survey. So this is what, if you had a wide-angle camera and you had really good clear skies and you integrated for a while, this is something that you might see. I'm only going to put on the lines because I know this audience doesn't need it, but that's because in a few moments I'm going to just switch from optical to infrared, and I want you to have a guide for how different the sky looks. So this is, again, Digital Sky Survey. This is what you see at 100 microns with IRAS. which is an infrared telescope. And it is a very different view. Just going to flip back and forth a couple times. So what you'll notice is Rigel down here completely disappears. All right? Stars do not make up the majority of this infrared light. What you are primarily seeing is the stuff between the stars. Some stars, like Betelgeuse, do still kind of pop out. I mean, it's not nearly as obvious as it was in the optical, but you can still see that there is some point-like light coming from there. But what you are primarily seeing with this completely different eye, all right, far infrared eye, completely different perspective, is the stuff between the stars. You can just make out some of the H2 regions, like Orion, and some of the ones on the galactic plane in the optical, but now they really stand out when you go to the far infrared, and then all the stuff that connects them to everything else. So you get a really different picture of the universe when you go to the far infrared. Now, IRAS was launched, I believe, in the 70s or 80s, so it was an older facility, and it did all sky mapping, but it had very low resolution. What Herschel gave us was the far infrared with a 3.5 meter, again, state-of-the-art, largest mirror in the infrared in space of its time, and at multiple wavelengths so that we could get images that look like this. So this is the Orion star-forming complex. For reference, since I'm assuming the people in this room have pointed their telescope at M42 maybe once or twice in their life, there's the Orion bar, there's the trapezium cluster. So this is more or less the M42 region that you know and love. Everything else is part of a much larger complex that you cannot see at optical wavelengths. You have to go to the far infrared to see it. These beautiful bubbles, all right, these filaments, these tiny little points of baby stars in the process of forming, all of this, the color, the structure, they all tell us very valuable information about how stars form and how this particular cloud is producing them. So this is why we go to far infrared wavelengths. Now, what we are specifically looking at depends on, what kind of objects you're looking at and what kind of instrument you're using. So in this particular case, what we're looking at is dust. Now, in the most cases, for those of you who, like to take pretty pictures of things in space, dust is sometimes a good thing because it can make your picture interesting, and sometimes it's annoying, it's in your way. So this is Barnard 68, which is this isolated small cloud, and it looks like there's a hole in the sky. That's because you got a dusty cloud in front of a star field. And the dust is really good at blocking the background light from those stars at optical wavelengths. So you got your background star, it emits light, hits a dust grain absorbs it, and that light doesn't reach us. So this is what happens at optical. If we go to near infrared, then our wavelength of light is a little bit larger. It can kind of permeate through the dust, and so now you can start to see those stars through the dust cloud. But when you go to the far infrared, what you are now seeing is the light from the dust grains themselves glowing. And that is the distinction. You are now actually able to directly measure light coming from this particular cloud when you go to far infrared wavelengths. And if you change your instruments, you can look at gas glowing at far infrared wavelengths. So that tells you some cool things about the chemistry. So far infrared gives us this very, very different perspective on what is going on in this particular cloud compared to if we only stuck to looking at the stars. Now, Herschel being a space telescope, you might be wondering, well, why do we go to space? Space is hard to get to, and you can't go and fix your instrument. I mean, you can if it's Hubble and it's in orbit around the Earth, but Herschel was at a Lagrange point 2. We're not going to service missions to fix things at Lagrange point 2, so why do we go to space? Well, let's take a look at what the infrared sky would look like from the ground. Not very interesting, is it? All right, we actually cannot see through our atmosphere far infrared wavelengths. Our atmosphere is really, really, really good at blocking light from coming in. And that's what's shown in this little cartoon here. So this cartoon shows atmospheric opacity, where 100% means it's stopped by the atmosphere and nothing gets through, down to 0, which means the atmosphere basically doesn't exist as far as that kind of wavelength of photons is concerned. And so at optical wavelengths, we have very low opacity, which means we get really close to the ground, or we basically can see it. And that's why when we're out at night on a clear day, which is not tonight, but on the next clear night, and you look up, you can see stars with your eyes, because our atmosphere is not opaque to optical light. But if you are interested in X-rays or UV, our atmosphere is incredibly opaque, which means you can't see anything. And if you're interested in the infrared, particularly the far infrared or submillimeter, our atmosphere, again, is really opaque and really hard to see things. And the reason why that is the case is because of molecular absorption, primarily from water. There are lots and lots of water molecules in the atmosphere, particularly on a day like today, and they are really, really good at absorbing certain wavelengths of light at far infrared wavelengths. So Herschel, which operates right at these wavelengths right here, from about 70 microns to 500 microns, is smack dab in that molecular absorption, removes everything from the ground. Therefore, we have to go to space in order to see things. And so that's what they did. In May of 2009, they launched Herschel. All right, so this is just a video showing that actual launch. This was an Ariane 5 rocket, and it was actually, Herschel was launched with another telescope called Planck. You might be familiar with Planck. So they were launched together, and they were both sent to Lagrange point 2 together. They didn't stay tethered together, but they were launched with the same rocket, and they were sent at the same time. So there you go. There's the rocket being launched back in 2009. For reference, I was finishing my master's degree around this time. All right, so I was starting my PhD right when Herschel was getting going, and it was just such perfect timing. It's great. All right, so yeah, and then you get the view of the people in the room. It'll go back to the rocket in a moment. So yeah, there's the launch of Herschel, quite some time ago. It was sent to Lagrange point 2, and this is again where Gaia is. This is where JWST is located. We'd send things to Lagrange point 2 a fair bit because it's a really convenient spot. It's 1.5 million kilometers from the Earth at a slightly further distance than from the sun than the Earth is. But it's at this very special gravitational point where anything in orbit about Lagrange point 2 is in lockstep with the Earth. So it actually follows the Earth in terms of its orbit. Normally, things that are further away from the sun take longer to go around. But because of the gravitational dance between the Earth, the sun, and the moon, what happens is objects at Lagrange point 2 maintain the same distance from the Earth as at all times. And that's convenient. It means that we always know where it is, and we're always able to communicate with it. So this is just an animation showing you the orbit that Herschel would have, and then you've got the Earth going around the sun, and you've even got the moon going around the Earth for reference. So just to give you an idea of just how it kind of has this lockstep connection with the Earth. So all telescopes at Lagrange point 2 have these sorts of orbits, and they all maintain the same distance from the Earth. So what was on board Herschel? We have 3 instruments, PAX, SPIRE, and HiFi. PAX and SPIRE did both photometry and spectroscopy, and HiFi was just pure spectroscopy. SPIRE and HiFi actually had Canadian contributions to them. Canadian instrumentation people helped contribute parts of SPIRE and parts of the HiFi instrument. And so this is where the Canadian Space Association's contributions to the Herschel Space Observatory really glowed. So I'm talking about a legacy because Herschel launched in May 2009. It reached L2 in July 2009 and basically started taking data almost immediately. It took data until April 29, 2013, so almost for 10 years ago. All right, we're just thereabouts, and so it had about a 4-year mission. All right, it did end because it had a definite lifetime due to the limited amount of liquid helium that was there for its coolant, and once it runs out of its coolant, it no longer was able to take data. But over the span of 4 years, they estimate that there was over 37,000 scientific observations that spanned more than 23,000 hours and covered about 1/10 of the sky. So this animation here actually is going to be a time lapse of all the data that was ever taken of Herschel mapped onto a sky. So you've got the constellations, you've got the ecliptic with the planets. The planets will move according to the time that is up here. And then you've got the galactic plane as this orange line here. So keep an eye on what happens with the galactic plane. And if you know where some of your favorite targets are based on their constellation, you'll see that you'll see if they get filled in at all. But you'll notice that as it fills in, it will fill in with different colors, and those different colors represent different instruments or different observing modes. And so you'll notice certain modes cover larger patches of the sky than others. So here we go. All right, so it's July. This first bits of data are starting to be taken, and we're filling it in. So you'll notice, it's basically filling in pretty evenly all across. It's not like it's only looking at one area, and that's because it's a space telescope. We don't have to worry about day-night. You'll notice galactic plane is starting to get filled in. Large areas over here getting observed. And we're at 2011 now, so we still got a couple years to go in the mission. You can see where, the large and small Magellanica clouds are, and again, more of the galactic plane is kind of getting filled in as time goes on. But yeah, for the most part, science observations were taken by many different groups of people with many different science goals, covering a huge patch of the sky. And so this is when the final observation was taken. So this is a snapshot of everything that Herschel ended up looking at in one shape or another. Again, the different colors representing different modes of observation. So yellow here is when Pax and Spire were used in parallel mode. So they were both used simultaneously. For example, I think orange is the hi-fi, or maybe blue was hi-fi, but you can see how the different colors represent different things. So the larger maps are all in the Pax-Spire parallel mode, because those were the ones that could do faster scans, and so you could do larger maps more easily. So with that, let's actually look at what some of the things that Herschel looked at. And to kind of preface this, Herschel did a lot. And in the time that I have, I cannot cover all the science and all of the cool results. So if I'm missing your favorite image or if I'm missing your favorite science area, I do apologize. But this is to kind of give you a snapshot of what Herschel was able to do over the span of 4 years. And I'm going to organize this from small scales to large scales, more or less. All right, this is not Herschel, this is Hubble. This is Fomalhaut, which is a debris disk around a young star. So the star is actually being massed out, and what you're seeing is light being scattered off dust in this debris disk around the star itself. So this is what Hubble saw. This is what Herschel saw. So Herschel doesn't have as good resolution as Hubble because of the wavelength, but again, you're seeing the dust grains themselves glowing. It's not scattered light, it's emission from the dust itself. And so you can really see this beautiful ring around Fomalhaut, very nice and clean, and it actually shows that there's a deficit of stuff in between. And so that tells us something about how dust grains get pushed away by the star, all right, through stellar winds and so forth. We also know that the observations tell us something also about the size of the dust grains and the structure of them. So the dust grains in the debris disk of this ring are likely quite large and fluffy. And with collisions, they can replenish and create smaller ones again and again, because otherwise all the small dust grains would disappear. And the fact that they haven't disappeared means they have to be replenished over a course of time. So understanding disks and debris disks was something that Herschel was able to do quite nicely. Another thing that Herschel did was be able to weigh disks, actually tell us how much mass there is in them. the most abundant atom in space is hydrogen. The most abundant molecule in space is molecular hydrogen. But we can't actually see molecular hydrogen easily because you got a hydrogen atom and a hydrogen atom, and they're equal. So there's no dipole between them. And if you have no dipole between your atoms, it makes it harder to have low energy transitions. And since these things are not in particularly hot environments, they don't tend to glow easily in molecular hydrogen. So how you can get around that is you replace one of those hydrogen atoms with an isotope of hydrogen called deuterium, where instead of it just being an ordinary proton, it's a proton and a neutron. And deuterium is something that is really hard to observe because you essentially have to go to space to see it because of its wavelength. Its wavelength is around 100 microns, all right? But they detected deuterium. This is a deuterium detection towards a disk called TW Hydra. The disk in the background is an artist image. It's not actually TW Hydra. It's just a pretty picture. But this is an actual detection of hydrogen, deuterated hydrogen, molecular hydrogen gas in TW Hydra. The J equals 1 to 0 just tells you what transition of HD it was. And then over here, you also have a high energy carbon monoxide transition with a much larger transition number that just happens to be at a comparable wavelength. And what was really exciting about detecting this is I think this was like the second detection of HD ever and the first one in a disk ever. So like Herschel made this possible. But what this showed was that all of our estimated disk masses based on using carbon monoxide, which is easy to detect from the ground, it's at 3 millimeters, so we can see it even on a bad weather day like this. And on top of that, the disks glow quite brightly in carbon monoxide. So all of our disk masses based on carbon monoxide were low. Basically, carbon monoxide gets depleted. It's missing from the gas phase in the disks. And what HD showed us is just how much carbon monoxide is locked into the dust and can then form organic molecules, for example, down the line. So this was a really, really powerful result because it completely changed our understanding of how much mass a disk has and then how much planet formation potential those disks have. Another important molecule for life is water. We don't know how water got to Earth, not entirely. We've got theories, but we don't really know. And detecting water from the ground is hard because the water in our atmosphere blocks light. So we were not going to see water from space through water on the Earth's atmosphere, basically. It's really, really hard. But if you go to Herschel, you can see water. And so here's detections again of water. This is another detection for TW Hydra of water. This is just showing you two different transitions in two different flavors of water, one being the para and one being the ortho. And then here is a map showing an outflow. So this is a young star that's releasing tons of material at very high speeds away from it. And this is water tracing along that outflow in a very young star called L1157. And so this is just a spectrum, but this is an actual map of it. So finding water not just in disks, but in the environment around them, horribly valuable in order to understand, the pathway of water, how water can get to disks, how water then evolves in systems, and then ultimately how it ends up likely getting onto future planets. On slightly larger scales, there's star formation. So I showed you that beautiful image of the Orion molecular cloud earlier, but we have beautiful images of lots of different molecular clouds. This is just a zoom in of Orion. So here you've got the bar, and here you've got M42. This is where the trapezium cluster sits. And then you've got this beautiful structure of cloud above it. Herschel had the resolution and the sensitivity that we could trace the entire cloud down to individual star-forming pockets, and which is really, really, really beautiful. So each of these little pinpricks of light are young stars in the process of forming, and so we're able to see the environment around them as well as those individual systems. And we've got like these beautiful networks of filaments. You can see these bubbles that show up in certain like tiny little pockets. And an important thing to note with all of these images, they are all false color images. You've got red, green, blue that's being put together in a computer, but they're not red, green, blue as your eye would see it. They're red, green, blue using different channels from Herschel. So the observations here, blue is 70 microns. All right, green is going to be 160 microns, and red is 350 microns. Over here, blue is 160 microns, green is 250 microns, and red is 350 microns. By doing things in that order, the colors actually have meaning. Red things are cold, blue things are warm. Now, when I say cold, I mean like 10 Kelvin, and when I say warm, I mean like 30 Kelvin. So it's not a huge range of temperature, and it's not, warm is, comfortable. They're all very, very cold. But we can see this difference in temperature based on the difference in color from just these images alone. So already we can piece together some really cool things about how, young stars impact their environment just by temperature alone, looking at these colors. And not to mention, Herschel made molecular clouds really, really beautiful. Like, they are just stunning to look at. These are some of my favorite images. We also got to see a lot about cloud structure, and Herschel really allowed us to understand filaments, their significance in star formation, their ubiquity in molecular clouds, and their properties. And so, for example, here's an example of a filament in Taurus. Here again, you've got the Orion B cloud over here. So there's the Horsehead Nebula, for those who are familiar with the Horsehead Nebula, glowing instead of seen in extinction. And then IC 5146 over here, again, filamentary structure. And one thing that was also found is that at a lot of places where filaments meet, you see this burst of star formation activity. So we've got this hub system where you get lots of filaments that come together, they create a hub, and you just got this burst of star formation that tends to be at these intersections of filaments or these hub-like environments. You can see, again, here, a whole bunch of filaments kind of coming together right where you get this burst of star formation activity. Again, some of my favorite images, high mass star forming regions. You've got the Rosette, or a section of the Rosette Nebula over here, and then you've got the Eagle Nebula over here. You may be familiar with this feature right here. These are the pillars of creation that Hubble made very famous, but again, now we're seeing it glowing. And so what you're seeing here is, high mass star forming regions. We're able to, again, the red, blue, green, show us where things are hot, where things are cold. But we're also able to now see the structure of the clouds and how, clusters can carve out these pillars, and then how they can influence the pillars, and we can start to see triggering. We can start to see the feedback mechanisms of hot stars and what they do to the molecular clouds that surround them. So there's so much cool stuff that comes out of these observations. And then there's just the wealth of data that exists for the galactic plane. So this is an animation that's actually going to go through and show you the Herschel Infrared Galactic Plane Survey, which is known as HIGAL. I'm not going to play the whole movie because it's 10 minutes long. It's quite long. All right. Basically, they did a 2-degree swath, so it's 1 degree above and 1 degree below the galactic plane, and they observed that in the Pax and Spire bands, so together, and they covered about 40% of the galactic plane. So they didn't get everything, but they did cover a huge chunk of the galactic plane in all of these observations. So these particular maps are being created at 70, 160, and 350 microns. I'm just going to skip ahead. Oops. Just give you an idea of just how things look. Again, it's 10 minutes long. I'm not going to show you the whole thing. Let's see if we can get to the galactic center. But you can see these bubbles. All right, some of these are H2 regions. Some of them are planetary nebula. Some of them are supernova remnants. There's so many different cool features that we end up getting. I think now we're approaching the galactic center. Yes, now we're approaching the galactic center. Then you get the cool activity that happens in the galactic center. You got the central molecular zone. This is a 100 parsec inner part of our galaxy where everything is crazy because you're close to the supermassive black hole, and so you're being tidally compressed, and you're forming star formation, quite rapidly, and the clouds are in all of these weird pressure states and temperature states, and they don't look anything like clouds in our nearby neighborhood. Again, 10 minutes, I'm not going to show the whole thing, but you get an idea of just how much data there are. So much work is being done even just analyzing one tile of these, 2 square degree tiles. But ultimately, there is so much that we are learning about our own galaxy and its structure through this particular survey. Looking at more concepts, we've got just looking at dust and understanding dust. So here you got dust from young stars, protostars, and then here you've got a planetary nebula. All right, and so you're able to get spectroscopy, for example, of this planetary nebula, and this is telling you how stuff that's released by the dying star can be reprocessed and turned into the next generation of interstellar dust. And so you got the ingredients there, and then you're able to learn more about the formation of dust, and then the evolution of dust as we study the young protostars. Very fun things. This is NGC 1999. This is the Keyhole Nebula, and Herschel confirmed that this is actually empty. For a long time, people thought maybe it was just an infrared dark cloud, and it was just very dusty and cold, and therefore just didn't emit, but Herschel sees it as empty too. So it's probably a section of a cloud that just got everything thrown out of it due to jets and outflows from young stars. But yeah, it was like a fun little result that came out from this particular set of observations. Of course, we looked at other galaxies as well. This is the Large Magellanic Cloud, again, as seen by Herschel, using multiple wavelengths from Pax and Spire. The red in this image is actually hydrogen gas, so it's not Herschel observations, but it's just to kind of show you the diffuse stuff. But again, you can see how structured the Large Magellanic Cloud is, and this is something then we need to be able to understand, what the impacts of the other aspects of the LMC happen to be in terms of, carving out this very complicated web of structure. And then over here, you've got the Andromeda Galaxy. Here's an optical image for comparison. So again, you're really just focusing in on the dust in the plane, because that's primarily where you're going to see dust. And then the blue stuff here is actually X-rays. So this is from a different telescope, just to kind of highlight the difference between the dusty disk and then where the clumpy X-ray stars happen to be. So again, we're able to study not just the properties of the stuff between stars in our galaxy, but in other galaxies too. And you really also get to see where the spiral arms are and the next generation of stars are going to be in these galaxies. Another thing that Herschel did a fair bit was look at blank spots of sky. Right? Hubble did this to you, JWST did this to you. You look at a boring patch of sky, you stare at it for a really long time, and out pops a whole bunch of really far away galaxies. Well, that is what the Cosmos field here is. This is from the Hermes Consortia. This is a patch of sky that has been very well studied by lots of instruments, and this is the Herschel view of it. It is again, boring patch of sky, but every dot that you see there is a galaxy. So, there are thousands of galaxies in this one tile alone. And they are primarily really, really, really far away. And as you look at things that are really, really far away, you want to go to longer wavelengths, because that's where the light is going to be most easily detected. And if you were to pick some of these patches of light and you were to zoom in on them with a higher resolution, such as with Keck, you can start to see the morphology of the galaxies that are being captured by Herschel. All right, but this is hard to do over the same patch of sky. So Herschel is telling us something about the number of galaxies that have a certain brightness at a certain distance, and then they can be followed up for higher and higher resolution. So this is, again, a snapshot of all the things that we were able to do with Herschel. As I said, it is a was and no longer an is in this presentation. This may have been the last image ever taken of Herschel. There it is, right here. All right, this was taken by the Fox telescope as Herschel was being moved from its L2 orbit to a heliocentric orbit. So it is now in orbit around the sun in a purely heliocentric orbit, so it's just no longer in lockstep with the Earth. It's much, much further away. They call this a parking orbit. They had to move it out because you have to maintain some sort of orbit in the L2 position, otherwise you were unstable. And if you're bringing in Gaia and you're bringing in JWST, you don't want other telescopes kind of filling in that space. So once they discontinue a telescope, they kind of move it out of the way. And so that's what happened here. That said, every now and then Herschel will swing a little bit closer to the Earth as our orbits kind of line up. And so in the next few years, it might come by a little bit closer. I don't know if it'll be close enough for us to image. I don't believe it will get as close as it did at L2, but it is something that I imagine people will try to look for. So yeah, this was, I believe, taken summer 2013 as it was being pushed to a further orbit. So I hope I've convinced you that the far infrared gives us a really cool picture of the sky, a very different perspective on various different sciences that have to do with the universe. Primarily, you're looking at things that are cold. As I said, we're looking at 10, 30 Kelvin. So, if you want in degrees Celsius, you're looking at about, minus 263 degrees Celsius. Pretty cold. But this is why going into space is valuable, because we want to be able to capture this kind of perspective in addition to all the others. And Herschel really paved the way. Its legacy is not yet over. I want to make it very clear. It has unprecedented data in its archive, which are publicly available if you want to just kind of play with it. And you can get images of disks, stars, clouds, other galaxies. And the data are all beautiful, is all I can say. So there's a lot of work that still needs to be done to analyze all these data, and there's more science that's probably going to come that I haven't touched on. But I think I've filled my time, and I'll leave you with just some of the pretty pictures again.
Are there any questions from anybody?
Oh. I don't know. Who wants to go first?
I'm just curious, when you said the filaments are combining the four stars.
Yep.
Do they see the Doppler shift or whatever that they're moving in as opposed to moving away from the stars?
Yeah, we definitely do have velocity gradients, so we can definitely use the Doppler shift. Typically, that's done with other instruments, so you would follow up these observations with a different instrument that is a good tracer of how those filaments are moving. And we do see that they do appear to be converging where the hubs happen to be. And so what people are interested in is how much mass is flowing along those filaments, how much mass is being fed into those clusters of stars that are forming. And that is hopefully going to tell us something about how big clusters of stars end up being born together. But yes, that is something that is being done. I don't have any pretty pictures of that because that's different telescopes.
Now that Herschel has passed on, are you going to be given access to web information?
Oh yeah, so Webb has different capabilities than Herschel. It's different wavelengths, first of all. It's more on the mid-infrared, near-infrared side of things. So depending on your science interest, you want to lean to you basically want data from as many wavelengths as possible, usually. But you might lean towards some of the instruments or others. So absolutely, I do hope to use Webb to look at regions like Orion, for example, to better understand the dust in those particular vicinities. But in terms of using Webb for the same science, I would actually use it for different science in that respect. Archival-wise, a lot of Webb data is public, at least the first releases are. And then some of it is proprietary, which means the people who ask for it kind of get first grabs at it. But once it becomes made publicly available, then anyone can use it. So if there is a target of mine that I would like to have Webb data for and it's available, I would certainly use it, 100%. Yeah.
You mentioned the Orion bar a couple
Yeah.
of times, and that's something I've not ever heard mentioned before. I'm wondering, is that something that's dark in the optical?
Ah, so the Orion bar is right here. So you probably are familiar with the trapezium cluster with M42, and then there's this kind of like this sharp edge. All right, at the southern corner of where the trapezium cluster is. That's the Orion bar. It's what we call a photon dissociation region. So it's kind of at the edge of a molecular cloud where you've got this cluster of hot stars. They ionize, but they can only go so far. And so it creates this nice sharp edge. And so that's what we call the Orion bar. It's just basically that nice sharp edge that you see in M42. Yep. Yep.
So just to clarify.
Yep.
So if like I do, I see M42 as a fan shape.
Yes.
So it's the hard edge of the fan,
It's.
not the wide dispersed.
I had an image from Hubble of M42 at one point in this presentation, and then I removed it, and I wish I kept it. So the fan shape that you're probably, because if this is north, okay, pointing up is north, if the fan shape kind of sweeps like that, then it is kind of like this flat edge. So it is probably the side of your fan and not the curved part of it. But yes, so that is a special region, because what it does is it kind of protects everything behind it from the ionizing photons. And it is this unusually sharp edge. Not all of these regions are as well defined. Horsehead Nebula also has one of these nice sharp edges, as you can see here. And you might remember the Webb picture of the Horsehead Nebula that had that beautiful transition. All right. So this is another example of where you've got, stuff ionizing, and then you have this sharp transition, and then over here you've got molecular gas. So the idea is you're seeing this phase transition. You're going from hot to cold in a very, very narrow transition. And that narrow transition is that sharp edge. It's what we would call the Orion bar for the Orion Nebula. I don't think it's got a fancy name for the Horsehead Nebula, but you can see that there's like this, there's nothing and then there's stuff. All right, and that is the transition.
Any more questions?
I've got a question. I love your enthusiasm. Wow. On one of your first slides, I think it was an image of Fomalhaut.
Yes.
And I would expect the dust ring to be symmetrical, but the intensity was not. Is that a Doppler effect that we're looking at here?
This could actually be a geometry effect.
Yeah.
All right. This is probably more of a geometry effect where, depending on, inclination, you might be seeing through more stuff along one side and, not through the other. That said, we do know that some disks have what we call dust traps, which means they do not have equal distribution of dust everywhere in the disk. So it is possible to have cases where you have a disk of stuff around a young star, and then there's this, for whatever reason, we don't know why, a pocket of more in one corner. And that is an unexplained thing at the moment. But I don't believe that's the case for Fomalhaut. I do believe that it is more of a geometry effect.
The universe hates symmetry.
So that being said, with the light that's in the bottom part of the ring, it's more than the top part.
So there actually are potential planets in the debris disk, so there could be some perturbation that's happening there. There could also be a temperature effect that comes with the geometry, where if you have a side that is, coming towards you or away from you, and the star is heating it, you'll see it front lit or backlit. And so there could be a temperature effect. There could be, line of sight, how much dust are you seeing effect. And there could also be, little bits of differences actually in the amount of dust that comes from planets. There's no reason to think that also everything should be perfectly uniform. I mean, as pointed out, the universe is never that kind to us. Yes.
Okay.
But yes, no. I mean, some of this is real, I imagine, but some of it might be, optics of just how the system is oriented. We have definitely seen, brighter along the edges due to just geometry alone.
Any other questions? I know I'm never going to look at a burrito the same way again. And
All
we
right.
also have homework to do. We have to go back and look at our sketches and our images of M42 now. Now we have to find the bar.
I can grab it for the 5-minute break, and we can. I've got it on another presentation.
Okay, great. Okay, thank you, Sarah, very much. Okay, folks, we'll take our 5-minute break now.
So the sky for May. Can we get the lights down? Here, room PC dock in. No, I don't know.
Oh, okay, fantastic. I'll give it back to you. Super, thank you.
Uh-oh. We're backwards. No. Oh, okay. All right. BAA events. This one's going to be on YouTube channel on the 5th of June, just before our next meeting. I can't remember what meeting this is now. Spring meeting or something. Anyway, talk on craters on the moon, amateur detection of radio pulsars, and somebody else presenting stuff on what's up in the sky. But you've got me, so
Tim is very good. You could ask for anything more.
that's right. AVSO webinars. There seems to be more stuff coming up now with the AVSO. The eclipsing binary section is having meetings now. I think the 11th of May is their first one. Also on the 11th of May, a how-to webinar. Unfortunately, most of us are going to be at Science Rendezvous, but filters and photometric transformations, something very useful if you're using proper filters in your photometry. Then on the 1st of June and the 8th of June, they're going to have brief reports from the various observing sections, solar, eclipsing binaries, and long period variables on the 1st, and then on the 8th, exoplanets, young stellar objects, and the instrumentation and equipment section. So those should be very, yes?
Do we want to talk about what's on right now?
Well, no, we missed it.
Okay.
There is the spectroscopy section meeting, which some of us would really like to go to or listen to, but unfortunately it intersects with our meetings or our Zooms.
We're trying to get it recorded so that they'll put it online.
Yes, that would be great. Lennox and Addington Deep Sky Viewing Area has a laser-guided star tour this weekend, Friday and Saturday evening, and again on the 7th and 8th of June. Got those out of order. 1st of June, astrophotographers assemble. Probably a good place to go if you're a beginner and want to see other people's equipment, get advice and so forth. The North Frontenac Deep Sky Preserve, they've now changed the name or something, I think. I can't remember what it was, but I thought I saw something online that it sounded different.
Yeah.
Deep Sky Observing on the 10th and 11th of May this weekend again, and 7th and 8th of June. They are also having afternoon solar observing from 1 till 3 on the 7th and 8th. Oops, what was that? Oh, what happened?
Wow, we don't have any nighttime.
No, something must have gotten linked in rather than stuck in. So I'm not sure this is even correct either.
Looks correct.
Sure looks like it.
Only 4.5 hours of astronomical darkness? That doesn't sound, no, I don't think that's right. Anyway, it gets dark at night, light during the day. Not nearly enough darkness at night nowadays. Sky events. Mercury's at greatest elongation west. Unfortunately, with the very shallow ecliptic in the morning, it's going to be very low to the horizon anyway. 15th of May, first quarter moon. 16th of May, the straight wall, also known as Rupi's recta, will be visible near the lunar terminator that evening. I always think it actually looks like a sword. It's got a nice little handle and a guard and stuff. 18th of May, the moon occults Beta Virginis, also known as Zavi Java. This is a 3.6 magnitude star, which is pretty bright, so that'll be nice and easy to see. Probably be able to watch it in binoculars, maybe even naked eye, because it's disappearing at the dark limb. And then about an hour and a quarter later, it reappears at the bright limb. Same day is International, oh, and I should mention that's in the early morning of the early morning of the 18th. So you have to get out on the evening of the 17th and be ready for it. International Astronomy Day on the 18th. Full moon on the 23rd. Almost at full moon, the limb of the moon is only going to be 2.5 arc minutes from Antares. We're getting into a period of time now where the orbit of the moon will take it either right past or over Antares quite regularly for a year or two. So that'll be very interesting to watch. So about 10 o'clock that evening. Last quarter moon on the 30th. The 31st, the moon is 1.25 degrees from Saturn, which is kind of cool. And new moon on the 6th of June. Major planets, pretty much garbage for the next little while. They are now all in the dawn sky. And with again, the ecliptic is very low, so they're all relatively low to the horizon. Saturn at magnitude 1.2 is probably the only one you're going to want to look at. It's low in the east-southeast when morning twilight begins. Mars is very low, like 3 degrees or something at the start of twilight. Neptune is also very low and 8th magnitude. Weird things happening. Uranus, Mercury, Venus, and Jupiter are all basically too close to the sun to look at. Small bodies on the 17th of May, number 2 Pallas. So that's the second minor planet or asteroid to be discovered at magnitude 9.0. Will be at opposition in Hercules. I checked for the month and it doesn't go by any interesting deep sky objects. But it's a good thing to look at anyway, just to add to your collection of solar system bodies you've seen. And on the 3rd of June, the minor planet 43 Ariadne at mag 9.1 is at opposition. It's interesting that this was the 43rd discovered and it's about the same magnitude at opposition as Pallas. Any questions? Yes. Yep.
It's a little bit sort of deviating here, but in the lunar observing program, in the Isabel Williams observing program, they want you to record seeing the new moon as the young moon.
Right.
Well, we all saw the eclipse. So
Did-
I'm thinking we're covered there.
Did you actually see the moon?
Yes,
Did you?
I did see the moon. It was the moon.
The moon that went across the sun. We saw it. We all saw it.
There was a lot of glare from something else.
Yeah. Well, but I think you could say that about a lot of things. Well, the galaxy was there. There was just a lot of glare. And it was,
So have to be the test cases and submit it. And see what happens.
yeah.
That's what we saw.
Take a picture.
Yes, and
Picture suitable for that.
And actually, if you take a long enough exposure, one thing that a lot of people do is you take like a 2 or 3 second exposure of the totality, and you can actually see the Earth shine on the moon during the eclipse.
Then you could use that.
But yeah, and whether I don't know if you'd ever see that visually though.
If you get
So.
another chance, use your flash.
That's yeah. You have to wait for the whatever it is 3 seconds. So pop the flash, 2, 3, click. Yeah.
Fire the flash in the telescope.
There's a customer that
Yeah. Peggy? You no? Oh, Bruce, yes.
Yeah, I just wondered, did you say what the background photo
I didn't. No, this is the obviously morning sky from my dock a few years ago,
Yeah.
just with the moon and Earth shine, and I can't honestly remember what those two planets are, but so unfortunately, you can see, given the direction of the ecliptic here, this must have been taken in the fall, because the morning ecliptic is very high. Right now, the ecliptic is sitting down about here, and so all the planets are kind of lost in the twilight.
Oh, Rick? You were
Yes.
saying about the North Frontenac Dark
Yes.
Sky Preserve. It's called the North Frontenac Astronomy Park.
Right. Yes, there you go. North Frontenac, the NFAP. So,
So astronomical twilight is 10:20 tonight and ends at 3:45. So
okay, so 4.5 hours. Brutal. And we're gonna think about having a star party in a month.
It'll be a solar party.
Yeah.
Okay.
Thank you very much.
Thank you, Rick. Okay, Roger.
Where's Rogers?
It should be it should be on the lap
On the desktop?
Down there?
I copied it over.
That's one. Thank you.
There's more than one?
Well, there should be another one.
No, I see that one, that's it.
You just copied over the one file onto the.
Yeah.
Okay.
You'll have to fake it.
No, because I don't want
Or
to do
just
that.
run it from the flash drive.
Okay.
Yeah, we're gonna have to,
That's fine. So
well, it's not showing up on the.
that's the next step, right?
Yep. We'll just change the display settings to duplicate. Keep. You're on.
Okay. I'm not sure whether it was last night or I think it was yesterday evening. I sent out this particular picture, leaving it to people at the end to actually have a look at the picture to find out what the hell I was actually talking about. So one of the things that I was doing on Monday when I realized it was going to be clear was I had a look towards the east, because that's my darkest part of the sky, and I wanted to do a number of images of some asteroids, because I'm actually quite intrigued by them. And so to go ahead and get involved with that, one of the things that Malcolm has done is get himself a code for his observatory site, and I thought that's probably a really good idea. To do that, you have to take some images of asteroids, typically not the ones that just have single digits or even two, but typically ones that got at least 4 digits in there, because they're reasonably faint. So they want you to actually try and work for this. Is your observatory and your technique sufficiently good enough to be worthy of their attention? So I thought, okay, I want to have a look for some asteroids that are down around 15th, 16th, 17th magnitude, and take some images of them, and do it again on Tuesday night, because Clear Sky Chart says Tuesday night's going to be clear too, and then I could do it like day by day, and get that. So I started to have a look around the area that I wanted to have a look at, and I happened to spot that there was an asteroid there called Edith Levy, and I thought, wow, well, I wonder. So I went ahead and did a little bit of digging, and it says, when it comes to this, in the discovery announcement letter, it said that Edith Levy is the mother of the second discoverer of it. So I went, aha, okay, so I know who that is. That's got to be David Levy's mother. So I thought, I'm going to take a picture of this. David was feeling really lousy last week, COVID, because he'd been out with an eclipse, and somebody had passed it on to him. So I thought maybe I'll put a smile on his face. So I added this Edith Levy to the list of asteroids that I want to do. It's 17th magnitude, so well within the range of what I can detect, and add it to the list. So I go out on Monday night and take images of 6 different asteroids, and Edith Levy was one of them. So I get back on Tuesday morning, going ahead and going through all the images and the data that I'd taken, and pushing it through some software to go ahead and pick it out. But it seemed to be having trouble with Edith Levy, and so I thought, like, what the hell's going on here? Am I going to have to go back to old school and go hunting for blinking pictures backwards and forwards to find out what's going on? Because what the software was telling me where Edith Levy was not where I thought the telescope was pointed. It should be just about right smack dab in the middle. And the software, Tycho, was telling me it was way off to the side. And I thought, no, that's not supposed to be the case. So anyway, having a look around on this, I went ahead and made sure that the stars were all nicely bloated to make them easy to see. And I spotted this little streak not far from the center. I went, that's got to be it. And so I sent out the thing yesterday, and it's not actually. It's erroneous. And so with egg on my face, I stand before you chastened, because I went ahead and sent out like erroneous information.
Oh.
So it's called in here annotated erroneous, because it is. So I'm going to show you what yes, Edith Levy is indeed David's mother, as best as I can determine. Now then. Oh, way cool. Okay, so you've seen her, and now you're going to see her namesake as well, because I went through this. This is the original like stacked picture that I went, and you'll notice, those of you who are close enough to the front, that all the stars are blurred here, because I had the Tycho software go ahead and follow Edith Levy, right? So it was maybe not really what she desired. She is actually, however, right here, and that's the actual asteroid there. And this software that I used, ASTAP, which some people will know for going ahead and doing plate solving, can do so much more than that. And one of them is it will stack images, and then it will, if you so desire, annotate them. And so when I asked ASTAP to go ahead and stack all of these things together and annotate them, it went ahead and found David Levy. So ASTAP also agrees with Tycho, and which means I've got something wrong with my technique at the telescope, because it's not pointing where I want it to actually point. This should have been fairly close to the middle, somewhere around here is where it should have been, but isn't. So I've got a pointing error somewhere around 15 minutes of arc, which is like, ooh. I know, that's horrible. That's horrible. Right? I just give up doing this. I mean, I'm almost embarrassed to admit that. But either way, this was where I originally thought it was. By the way, was this little thing there.
Before or after you redug your pier?
This is as of like a couple of nights ago.
The new pier.
This is the new pier.
Mark says you need another new pier.
It's the new pier, the pier number 2, number 3 actually at this location. So I've got something I have to track down, and so which is really annoying, because it's going to be, we get like about 6 days of cloud, a day of clear, and another 6 days of cloud. And I'm going to be wasting one of those days of clear trying to figure out why is this happening, unless I can figure it out ahead of time. The telescope was properly polar aligned the last time that I went out prior to Monday, so I know that that's not an issue. Tracking was really nice. The stars are nice and round. It wasn't quite collimated or tweaked the way I wanted, but that's okay. The stars are relatively round. Oh, another nice thing ASTAT will do, it will show you the aberrations and the fact that you're, which way you have to tilt your detector
Maybe you
because
should
it's not
use this.
square on. Cool piece of software. Sorry?
What epoch is your telescope?
That was the other thing I wanted to go ahead and do, but everything was operating with JNow. So I had it all set, so it's using the epoch as it is supposed to be. But so the workflow that I go ahead and do is I have the telescope point where something like Carte de Ciel tells me Edith Levy is, and so it goes there, and then I take an image and plate solve it, and it says, okay, now I know I'm not actually pointed at Edith Levy anymore. I have to then go ahead and tell the telescope pointed to the new position. And it goes ahead and does it, and I plate solve that and says, yes, now you're pointed right in the middle at Edith Levy, right? I've stalked her. And yet, when I go ahead and start taking the pictures, it's not there. So I'm not sure whether, Rick?
I would compare the position that you've measured here.
Yep.
Against what Carte de Ciel is telling you where it is.
That was my thought too. So I actually fired up Stellarium and downloaded like all kinds of gigabytes worth of catalogs and spent a fair bit of time. But I made sure that I used the MPC DAT, right, from the Minor Planetary Center. I used it for both Carte de Ciel and for Stellarium, and they both agreed that that's where it was. So the telescope should have gone ahead and pointed exactly there.
The times
where the asteroid actually
This
is when you measure it?
Yeah, this is where it actually is, right? I'm hoping my telescope should have been pointed there, but it wasn't.
Whoa, okay, time's up.
There we go. So it turns out that it wasn't only just that one. When I got Edith Levy was the one I really wanted to go ahead and do. Unfortunately, Edith Levy's on the frame. 4 of the other 5 that I took aren't even on the frame. So I've got a pointing / plate solving issue that I have to try and go ahead and solve.
Your time is all set up correctly on your computer versus program versus.
Yep.
Bigger sensor camera.
Yeah, exactly. Yeah. More sensitive cameras. Yeah, my wife would be really happy with that. Anyway, so you know, these things are sent to try us. But it's not just the good things that we come here to explain, but this is really, really seriously bugging me. But I'll let you know what happened. My apologies for sending out the erroneous information. But at least next week, hopefully, I at least got David's mother on there. I'm sorry?
What was the other street?
It's actually a double star, very close together. And so it turned out that when I went ahead and increased like the exposure, like bumped up the noise, that these 2 close stars joined together. And so in this particular case, if you look at the original one, you can actually see there's 2 stars there. And that was what actually clued me in as to what had happened here. So I had to find other ways of finding Edith Levy. Anyway, thanks very much.
Thank you, Roger. Okay, Bruce.
To hold this or wear this microphone?
Sure.
Just hold it up, Bruce.
Yeah, you can hold on to it.
Okay. Nice.
Okay.
So after the eclipse, I decided I would just have a closer look at the moon. And so I'm in this short presentation tonight. I'll just be. I have my. I have 2 cameras. One is a DSLR, and the other one is a mirrorless camera. And I'm just wanting to see what level of resolution I can get. I'm not using a telescope in this round. that's another story, trying to get optimize how best to record the images. But this is so this is I was interested in this. I'll get down here. So I've got it's a prime lens, 135 millimeters, and it's fairly short exposure, and you know, I'm playing with the ISO to sort of keep the intensity of the moon down. I felt that I was starting to get some resolution of the you know, crater at the top, and I was interested in that because you know, we had actually seen some interesting, yeah. So there, right up here, the so I guess the you know, the diamond ring and then the little beads and so on during the eclipse, I was really quite interested in whether I could have a closer look at the surface of the moon and see where, and I think that I was beginning to pick up these up. This is the same evening with slightly different exposures playing with it. So in the next image, now here's the mirrorless, and so this is actually a different night as well. So we're actually, it's not quite full moon, it's a day or so after. And I'm again trying to, I played with the exposures a bit. These ones are actually set at exactly the same amount. And I don't think I was getting as much resolution here. Yeah, I played with it. And I guess I'm just wondering what, does anyone have any suggestions on how I can maybe try to increase or have better resolution?
You and me both, Bruce, because I need an image of a full moon to complete my certificate program. And I've been working at it for over 2 years. Because you only get one full moon, or maybe two a day on either side of it, a month. And you're either cloud or rain, or you're somewhere else and otherwise engaged.
Yeah.
So it's taken me a long time, and that's still better than what I have.
Well, that's a very positive comment. Thank you very much.
So which one is mirrorless and which one is the
Just pull it down a little bit. So this is mirrorless.
So you took two pictures with the mirrorless.
Yeah.
At the same focal length, same speed, same ISO.
Yeah.
Do you have any that you compared the two cameras with the same lens? Because that's how you're going to figure out.
Yeah. Oh, I see. Unfortunately, the so the mirrorless I have, the camera, the lens, the 135 doesn't fit, so they're not exchangeable between the two.
You have to get the special ring.
Yeah.
On the mirrorless.
Oh, yeah. Okay.
135 on it.
Yeah. Okay. Yeah. Actually, that's a good point. I can do that. Sorry? Yeah, and the same night. Yeah. Okay. Sure. Yeah. Anyway, I just wanted to. I just wanted to let you know I was trying to go. Listen, I sort of had my eye on this certificate, but I wanted to first of all get a little bit of experience. You know, just getting a photo.
I think that first 135 millimeter shot for 135 millimeter lens, to me, that's a nice picture.
That is very good.
That is, I mean,
you can really see the texture.
Yeah. It's interesting, the color. There's no. That's the real color it was.
Okay, so you had no neutral density filter or anything like that?
Yep.
No, no. Okay, so yeah, I was trying to bring down the
I would say the only way to get more resolution is more focal length.
Yeah.
Go up to 300, 500.
After the second one, this one's well focused. That's the first one.
Yeah.
Yeah.
So this,
If you put a filter in between, that would affect the focus.
This one to me almost looks like motion blur.
Yeah, and maybe it was a different night, so the might have been a little bit more
Turbulent.
haze or
It could have been
something
some
too. So,
turbulence.
yeah.
yeah, but
We're gonna have a lot of vapor in the air and a bit of a breeze.
Yeah, it's really it's tricky, isn't it?
how
It is.
Yeah.
are you pressing your shutter? Do you have a remote shutter?
I have a timer,
A timer?
yeah.
Okay.
10 seconds.
Because that's the only other thing that could cause motion
Yeah,
500th of a second, right?
yeah.
Okay.
So anyway, yeah. So I did like the one that had the
This is the,
you could actually see some
okay.
Good job, Bruce.
surface. Thanks very much. Yeah.
Susan? I don't know what it was you wanted, but the floor is yours.
So a month now.
You have a quiet voice. Use the microphone.
I have a quiet one. No one's ever said that to me before. So a couple of months ago, I asked people about the socials for the summer and what they wanted to do. So I just wanted to bring that up again and let me know if you want to do telescope clinic, if you want to do picnics, one picnic, one clinic, and the rest all virtual. Just think about what you want for the summer, and we'll we can always have choose a couple of weeks for a picnic, and then if we have to bump it because of weather or something like that. You know, we can be quite flexible, right? So yeah, so that's all I wanted to say. Just keep thinking about it.
The only thing, are you thinking of the telescope clinic for members or for the public?
For the public, yeah.
In which case advertising and stuff, it makes this
Yeah.
a lot less flexible.
Yeah, that's that. But that would be if we did one of those, that would be the only one that we would have to be really, you know. Yeah. Well, we want to encourage people to bring their equipment, right? So if it was in the park, it would be be best. Anyway, that's it.
Okay. Okay, well, we're coming up to the end of our meeting because we have everything presented. So check out our website. We got our Facebook group, YouTube channel. And if you're not a member of the Kingston Center, well, come on along and be a member. And so we'll see you next month here, this room, June 12th at 7 p.m. And Michael will probably be getting a hold of us about dinner beforehand. So now we've come to the end of our meeting. Thank you all for attending. We can chit chat now. If not, have a pardon? I don't know. You'll have to ask Malcolm. You phone him up in Chile and say, Malcolm. Okay. So, good evening, everybody. Have safe trips home or if you got to travel. And thank you for attending. And thank you, Sarah.